Hello everyone. Nice to see that you all want to hear about surviving telephony or how you can keep your app awake, for example, to ensure the safety of your users like we did when we implemented a use case specific GSM phone app. Before I begin, I would like to get to know you a bit. Who of you is an Android developer? Raise your hand. Yeah, obviously. Who of you has already struggled to keep your Android app alive and awake? Raise your hand. Nice. And who has implemented their own phone app on Android before? Good. And is there anyone who has had to deal with safety critical software on a smartphone? Okay, an interesting mix. I hope we'll have something for every one of you. We, that is my colleague Katrin Scheidemann, who unfortunately cannot be here in person today, and me, Peter Brandt. We're both software engineers at Ergon Informatik in Zurich in Switzerland. And there we recently had the opportunity to be part of the project team that developed quite an interesting Android app for a major European railways carrier. This Android app is used for voice communication between shunting team members of that railways operator. Let me give you some background information so you understand the environment where the app will be used. Shunting, or rangieren for the German speakers, is the process where trains are split into individual carriages and composed again into new trains, and this usually involves a shunting engine, like here. It often happens in a shunting yard, and it requires that the involved shunting team members communicate with each other, for example, with an old device like this. Shunting happens in teams of people, usually an engine driver and a couple of workers. Shunting takes place day and night all around the year, in any kind of weather, hot or cold, sun or rain or snow. The shunting teams work with heavy gear in loud, bright or dark and dangerous environments. Their safety is absolutely critical, and the same holds for the availability of their communication tools. Historically, shunting teams used to communicate via analog radio connections. Today, group communication via a digital network like GSM is used. Our clients wished to move away from use case specific bulky hardware radios to a consumer smartphone controlled by a custom-made hardware add-on, the so-called RSM device or remote speaker microphone that the users usually carry on their work jacket near the head where they can press buttons and hear and speak. To give you an example, typical shunting maneuvers can look like this, where the train moves to the right, being pulled by the engine. But it can also look like this, where the train moves to the left, being pushed by the engine, and the engine driver at the end cannot see anything and must fully rely on the information that the worker on the front of the train communicates to them. For example, to say, please stop in a few seconds or whatever. This is how it looks for the guy at the left who is at the front of the movement. And this is what the driver sees. Almost nothing, just sees the end of the last carriage. As you can clearly imagine, reliable communication and sound safety features are essential here. So, safety is important. What do we do in our app to get that safety? We ensure safety, especially during dangerous maneuvers, by turning on a so-called control tone. That's a short beep every few seconds that gets automatically broadcast into the voice connection by the RSM device. And if the driver does not hear that tone anymore, they immediately stop under the assumption something is broken, something must have gone wrong, I might not hear the other party giving me important information, so I better stop now. Another measure we have is the so-called tilt angle monitoring. We're making sure that the device is in an upright position in the pocket of the user or in the position the user started the maneuver in, and the user has not, for example, fallen down and the device is in a different orientation. We do vigilance monitoring, so we make sure that the user interacts with the app regularly and is not, for example, unconscious and not able to say anything anymore. We monitor the battery of both the RSM device and the phone regularly to ensure we notice early enough when the battery goes down. We do signal strength monitoring of the Bluetooth connection and the GSM connection, and we handle errors and inconsistent states in a very specific way. For example, if Android tells us a call is on hold now, but we don't expect it to be on hold, we handle and react accordingly. And last but not least, we give the user the possibility to trigger an emergency call, which then in turn causes a lot of actions to be taken in the app and in the network. I'll get to more details later. So you see that app, we call it Railcom app here. It's not just a simple dialer with a nice user interface to enter phone numbers or to mark your contacts as favorites. It's also not just another voice over IP money-saving telephony app. We're just using plain GSM telephony here, nothing special. But it's one software part of the next communication solution of our client, consisting of hardware, the smartphone on the RSM device, of software, our app, the RSM firmware and the backend, and of network infrastructure in between. We're fully replacing the default phone app on the telephone. Why do we do that? Compared to a regular phone app, like the one on the left here, there's a lot of use case specific business logic inside. For example, we've got functional numbering where users temporarily get assigned a second phone number based on their role and location where they're working. We have state-dependent automatic call accepting and call rejecting depending on what the user is currently doing. We've got remote configurability of that app, and we do local and remote monitoring of the operations. And important, we have all the safety features in the business logic layer that I mentioned before on the previous slide. The Railcom app makes a clear distinction between private use and on-duty or work use. Users are allowed to take the device home, so the employees of that railway operator can take the device home and use it for private telephony, for example, on the weekend. And in that case, in that scenario, there are only very few restrictions. The app is just a normal phone app, provides standard telephony functionality. You can connect any kinds of headsets and headphones to it. You can set whatever ringtone you want and the volume, or even set it just to vibrate. You can connect it to your car system, whatever you want. Once the user is working in the work use case scenario, however, when he's on duty, the app has a very specific purpose. It provides use case specific communication for shunting teams. And for that, users register on a team with specific roles in that team and communicate as those roles. There are high demands on audibility because the environment is very noisy. So only the RSM device can be used, no other headsets. We do push to talk, so the user always has to press a button or an on-screen user interface element to unmute the microphone. We've got constraints for volume settings of ringtones, for example, or of the loudspeaker, so it's not too loud, but also not too low, and the user cannot hear anything. And we automatically reduce interrupts in dangerous maneuvers. For example, we then reject certain calls which are not relevant at that moment. Luckily for us, the environment in which the app is used is a very controlled environment. We have to support only a limited set of device models and Android versions, and we only have to test on those. The app is deployed via a company internal device management system, so we're not affected by most constraints and requirements of Google Play or other stores. And the setup and the parameterization of the used phones is clearly defined, including which other apps are installed on the device. And the used SIM cards, they're provided also by our client, by the railways operator that runs their own phone network. Now that you know the baseline and some of the challenges that one might encounter when shunting trains, let's first focus on the main functionality of the app, which is telephony. So to give the users the possibility to communicate with each other by voice. And that functionality we achieve using GSM telephony on a railway-specific internal GSM network, also known as GSM-R. The R stands for railways. And after that part, I'll tell you how we managed to keep our app alive and awake to ensure all the safety features. Just in case some of you are taking pictures of the slides, I'll have a link at the end where you can look at the slides later if you're interested in them. Let's look at some typical telephony scenarios for shunting teams. In general, all members of a shunting team participate in a multi-party conference in the GSM network that the team lead initiates. Now, when another team colleague of the same team calls the initiator, then the initiator sees an incoming call and can either accept the call or reject the call. When accepting the call, the incoming call gets automatically merged into the existing conference call with the others. Not like with a normal phone, some of you might have done that before, where the conference would then always be put on hold when you take the second call, and then the initiator first talks to the colleague and then manually has to merge the call into the conference. That all happens automatically in that scenario. Now this does of course not happen with any callers, but only with workers who are registered on the same shunting team. If, for example, the initiator gets an incoming call from someone outside the team, let's say their mom is calling, they can accept the call, but the call does not get merged into the conference, but the conference gets put on hold, like you would be having that on a regular phone app as well, and the new call is then done as a one-to-one call and can be either hung up or only hung up, but not merged into the conference because the conference is for work purposes. Now let's assume that the shunting team is currently performing a dangerous maneuver like the one I showed in the beginning, and they do not want to be disturbed during that maneuver by incoming calls. So they set up the conference as normal, and then they indicate to the app that they're doing something critical. In that case, if the mom calls, her call gets automatically rejected by the app and not even indicated to anybody in the team. If, however, someone important calls, like, for example, the local railway traffic controller, their call gets automatically accepted and automatically merged into the conference because they might have something important to tell to the team which is doing that dangerous shunting maneuver at that moment. As you see, there are some simple automatic actions in the app already, but we went even further. There are several workflows in the app. They interleave the telephony handling on one side, communication with the backend and network, and the interaction with the RSM device. One example I want to give here is the emergency call. If one of the users has an extraordinary situation, they press a dedicated red button on that RSM device, and that then indicates to the app that the emergency call workflow must be started. And the app then does first turn off the control tone, which immediately indicates to the driver that something is wrong. And second, it broadcasts a special alarm tone and a message into the ongoing conference call, so all the users hear that. And third, the app sets up an emergency call to a specific location-dependent emergency number and automatically merges that call when it's accepted by the other end also into the existing conference. So all team members can participate in the emergency conversation and all can act as needed. How did we implement all that? The Railcom app implements Android in-call service and call screening service. And by doing that, the intent action dial is handled by our app. The stock dialer app remains on the phone and can still be opened by the user, and they can use the dial pad to enter a number, they can see the call history and the contact list, but whenever they want to do a call by, for example, pressing the green button in the dialer of the standard phone app, the action then gets transferred to our app and we do the actual calling on the network. The Railcom app is chosen as the standard phone app by the user, and therefore it also shows all incoming call notifications. We do active manipulation of the call history list, the call log on your phone. For example, a call that got automatically rejected in a dangerous maneuver will later be shown as a missed call. So the user sees I had a missed call during that time. It was not a rejected call. I'll go into more details now. the in-call service, for those who have never done telephony apps, Android binds to our custom in-call service instead of the one of the stock phone app when the device is in a call. Certain methods get called when a call is added or removed, and we can then register callbacks on those call instances. So we get informed about state changes of all the calls we handle. And by doing that, we can update our internal telephony state model we have, which is then reflected in the user interface. For example, when we open then the incoming call user interface when a first incoming call is detected. One important thing, if our app would crash, and it should not crash anyway, like everybody's app, then the in-call service of the stock phone app takes over all of the existing calls, and we later have almost no access to those calls anymore because we don't have the call instances as handles anymore, even after the app got restarted. The only thing that we could do then at that moment is to tell the telephony manager to drop all existing calls, which would in principle bring shunting to a safe state because the control tone gets cut off that way as well and the driver stops driving. Instead, we handled that case already earlier when in the on-card exception handler, and we switch off the control tone explicitly by telling the RSM not to broadcast it anymore. And then we disconnect not all calls, but only all non-emergency calls. So in case the user has an emergency call going on at that moment, they can still speak with the emergency call conference. How does the telephony handling work programmatically? Let me give you an example. We want to join 4 users into a conference. That is the initiator plus 3 more participants. First, we set up a call from the initiator to the first participant. And to do that, we tell the telecom manager to place a call to a certain number. Once that call has been set up, we get a callback on the in-call service telling us on call added, call 1 is existing now. Fine. Then we say, okay, place a second call, and we get on call added for the second call. In the background, the first call gets put on hold, and our callback also gets notified that the call is on hold. And then we also get a callback on the second call that its conferenceable calls have changed, and there's a list of conferenceable calls, so call 1 is then one of the conferenceable calls, and we can do call 1, conference me with call 2. And we get a call back again saying there has been a conference call added now. So at that moment, we've got 3 calls going on, the 2 individual calls and the special conference call handle. As a next step, we place a call to the third participant. We get on call added for the third one. Here we see that the state of the third one has changed to active, and we can add it to the conference at that moment. In the Railcom app, we also need to dynamically decide which calls to automatically reject and which ones to let through, like in the examples I gave you earlier. This can be done by implementing the call screening service. Whenever the operating system wants us to make a decision whether to reject a call, the on-screen call function gets called, like you see here. It can then analyze the details of the calls in question and our current app state. Are we in a dangerous maneuver? Are we in private use mode? And then make a decision which then gets returned by calling respond to call with an appropriately constructed call response object. And that object has attributes like disallow call, reject call, whether to skip the call log, and whether to skip notification, and so on. With the state-dependent automatic blocking or accepting of calls, the list of recent calls, the so-called call history, is not always showing what we want. 2 examples. So we've got some calls to internal technical numbers which we have to do from the phone to achieve certain behavior in the network. And we don't have those calls to appear in the call log ever, so the user does not confuse what's this weird number showing up in my call log. So when calls are disconnected, calls to those numbers are always actively removed from the call history using the content resolver for call logs. Entries from auto-rejected calls should be replaced by entries from missed calls. But still, we don't want to see don't want to see any missed call in the call history. We want to have a notification that someone had called. So we do it like this. We first manually add an entry for a missed call to the call history. Then Android adds or has added a history entry with type blocked, because the app told the operating system to block the call. And then when we add the missed call entry, as a side effect, the missed call notification gets updated by the operating system, and the notification badge on the app icon also gets updated with the new number of missed calls. And only then afterwards we can remove the blocked entry that has been generated by Android, and from the point of view of the user, it looks like it should look. So telephony is one part of the app. But for many of our safety features, the app has to stay alive and awake in order to react appropriately. How this is done, I'll show you in this next section. So our goal is we want to stay alive and awake. That means even when the screen is off, even when the phone is in the pocket, and even when the phone is stationary, and all that can happen in the work scenario because shunting workers carry the phone in a special pouch, and they interact usually only using that RSM device, not directly on the screen. Then even in that scenario, the app must still not be killed by Android, and it must stay awake in order to ensure the safety of the users with all the measures like tilt angle measuring and vigilance monitoring. And it has to do correctly timed interactions with the telephony, for example, in the emergency workflow, where certain steps have to happen in certain order with certain delays in between. And the app has to allow remote app interaction via the RSM also anytime, and the app, if the app is sleeping or even killed, it wouldn't get anything, any notifications from the RSM. If you come from a desktop or a server background, you might think, so what? I'm running all the time. But for all of you who have lived in the mobile world long enough, you're probably aware of all the mess that modern devices are doing to the apps in order to squeeze out a few more minutes of battery life. So, what can we do? Let's start with the basics. According to the documentation, and I quote, the system can kill the process at any time to reclaim memory, and in doing so, it terminates the spawned threads running in the process. And to determine which process to kill, when low on memory, Android places each process into an importance hierarchy based on the components running in them and the state of those components. The importance hierarchy is also listed in the documentation. Top of the hierarchy is the current foreground process. That's the one the user is currently interacting with. And that obviously is only killed as a last resort, because if that happens, then the user cannot do anything with his device anymore. Second in the hierarchy is any visible processes. For example, if your foreground process activity does not fill the whole screen or is half transparent and you see any other activities behind it. And amongst those visible processes, visible in quotes, are also foreground services. For example, the music player, and thereby the foreground service is treated as something the user is actively aware of. Third in the hierarchy are simple service processes, and the fourth level are cached processes, which are currently not performing any work. So Android would primarily start from the bottom, killing cached processes, then service processes, and so on. And if you don't do anything in your app, and the app seems to sleep in the view of Android, then your app process will quickly end up in level 3 or 4, and you might be killed, which is not good in our scenario. In addition to that official hierarchy, at least in our experience so far, Android has mercy with apps that are an active device administrator. So not even the normal user can force stop it when you go to the app settings and you've got a device administrator. It's running, but the force stop button is grayed out. The app that has a bound telephony service, that means it handles at least one incoming call, usually doesn't get killed. And also an app that is an active accessibility service, but we're not using that because that topic opens a whole new can of worms, as some of you might have seen if they've been in here with the previous presentation. And there's a few more which I've come across in the past, but we also didn't have to make use of those. So what do we do to keep our app alive? So we enforce that our app is an active device administrator, and we can do that because we're not a mass application, but a specific work application for our clients. We start a foreground service and show an ongoing foreground notification. Although also that just got a bit more difficult. Apps targeting SDK34 and later need to specify a valid foreground service type. And the Google Play rules enforce that we have to go up with the target SDK, which we are luckily not so fully affected by that because we're in a corporate app store and only distributed internally. We also declare our app, obviously, as the default telephony app, and we implement those services that you saw before. And the user, when starting the app for the first time, tells the app and the operating system, I want you to be my default telephony app. That then leads to the system binding to our telephony service, which keeps the app alive as well. Okay, now we've reached the state that our app process does not get killed by Android, but it might still not get any execution time. So it's alive, but not awake, sleeping. And we don't get any CPU cycles. For example, when the device goes to sleep, which, by the way, is quite probable, as I said, because in most use cases, the shunting workers have the phone in a pocket with the screen off, and they only interact using the RSM device. And then the app shows some really bad effects. For example, coroutine delay returns much later. So for example, you request 2000 milliseconds, and then 3 minutes later you wake up and you can do something and you saw that you've missed what you should have been doing. And that, of course, impacts our application logic. For example, we have no vigilance control anymore, where we need to make sure that the user regularly interacts. It impacts the emergency call workflow, which is also a safety problem. And there's also no reliable reset for some of the warnings that the RSM device would audibly spit out, which then can lead to distraction of the user. Probably also affected is thread.sleep, where you return much later. And we don't get any gravity sensor values delivered anymore when the app is sleeping. That means we're not able to do the tilt angle monitoring anymore to ensure the safety that the user hasn't fallen down. And all of that can really happen, and indeed did happen, as I said, when the screen is off and the device is seemingly unused, which is our main use case, unfortunately. So how can we make sure that the device and the app stay awake? What about some coffee? Well, we can do the Android equivalent of coffee. We can request and hold a partial wake log. All good, until the device goes into doze mode, which, according to the documentation and reality, breaks wake logs. So are we back to square one? No, we're not, at least if we use some magic, and that magic is called ignore battery optimizations. That can be set for an app by the user, and it helps then the wake logs to keep the app awake because they don't get broken anymore during doze mode. It also prevents that the app drops into lower standby buckets, which are also a completely new kind of worms. I'm not talking about these details at the moment. But that magic comes with the usual Play Store constraints that only apps that are declaring that permission to request ignore battery optimizations, they're only admitted to the Play Store under certain exemptions. And one of those exemptions is the app is a safety app, apps that keep their users and their family safe. I think that would apply in our case if you've seen the use cases before. But since we're not in the Play Store anyway, we're not really affected. But I'm just telling this to the ones of you who are thinking of doing a safety app in one way. What are some of the oops moments we had during development? One was, if you're keeping ADB active during development and during your tests, that's not a good idea. Because while you do that, everything looks super fine. But many of the negative effects, like the app is not awake, they're only observed when the device is not charging and when ADB is not active. And ADB not active also means you cannot use ADB wireless debugging, because that also keeps the app interestingly awake and everything seems fine. And another one which we stumbled over was if you acquire a long-lived wake lock, before you request ignore battery optimizations, that might lead to having those wake locks broken anyway, even after that you have ignored the battery optimizations. That was at least our experience we had. But if we cannot use ADB, how do we debug then? Well, we can log to a file ideally. For example, we log periodically the battery level or sensor values to later see in the log file gaps which might have happened during when the app was sleeping. We log to a file because ADB is not connected and the internal logcat buffer of the device might be too small. That's one very crude approach, but what helped me really much was the battery historian tool. It helps a lot to visually analyze the huge files that you can get if you do ADB dump sys battery stats and ADB bug report. It shows you, after the fact, tons of information like wake logs, dose mode periods, battery drain, ongoing phone calls that had been running. How do you use that? There's a Docker image, and I really recommend that to use that. That's the easiest way to get it running. You can also compile the Go code from source if you desire so. Then you run your app on the disconnected device and tell it to collect all that information. And afterwards, you connect the device, dump the battery statistics from the device, and upload them to the battery historian tool running in your web browser. Unfortunately, hello Google, it seems that the battery historian has now reached the ends of its maintenance life. What a surprise. But at the moment, you can absolutely use it. So the Docker images exist, you can use it, it's working, and I can really recommend it. As an example, how does the output from the battery historian look like? We see a lot of information here, graphically and as text, a lot of very small information. We don't only see the battery drain, but also like the held wake locks and how long they've been held, the screen on time and off time, active dose mode when it was there, any ongoing phone calls, mobile signal strengths, and much, much more. And of course, also the battery drain, that horizontal line going down here. That's really useful when you want to know what your app did while the device was disconnected or what it did not do and you thought it should be doing when the device was disconnected. And we get an estimate where the used battery capacity went. Here it was mostly a very long ongoing call, contributing to about 40% of the battery consumption. Talking about battery consumption, wouldn't all those tricks to keep the app alive and awake have a horrible effect on battery life? Especially, what's the impact of that long-running wake clock on battery consumption? There's one way to find it out, measure it. So we did a test setup, we used a new device, we had the battery charged to 100%, we disconnected it, we ran the app for 9 hours, which is approximately 1 work shift of the railway workers. We had the RSM connected, the screen was off, the device was not moving, there was no interaction with the app directly. And we did that 4 times in total in 4 different scenarios, with and without a permanently ongoing phone call over those 9 hours, and with and without the permanently held wake clock. So we could compare the impact of both of those factors. We had direct observations, we had the power consumption in battery historian, which you could look at, and we had indirect observations in the app logs. So we saw that only when we held the wake lock, we had regular log entries, for example, of the battery log for over those 9 hours in regular intervals. So what are the results of our measurements? The results are great in the eyes of our client. First, the 2 bars at the top. When there's no ongoing phone call, after 9 hours with the screen off and the app active, but maybe not being awake, the battery fell to only 97% after 9 hours, or to 95% in the case of a permanently held wake lock and the app actively logging stuff during that time. With the long 9-hour phone call, that's the 2 bars at the bottom, that phone call contributed mostly to the battery drain, no surprise. But nevertheless, after 9 hours, the battery was still at 71% or 68% in the case of a permanently held wake lock. So what can be seen? The permanently held wake lock only contributed to additional 2 or 3% of battery loss in our case. Okay, we don't do much in the background. We mostly sleep ourselves. But what we do is essential, and it's critical that it happens exactly in the moment when it should happen, and we've got full control over that. And this last variant is indeed the variant for production now, starting with a fully charged device at the beginning of a shift and having still 68% of battery left after 9 hours, including a permanently running phone call for 9 hours, was a great result for our clients. Now let me come to a conclusion. As a summary, what did we learn from our journey? We learned, not really unexpectedly, that telephony has a lot of uncharted waters. The documentation is a bit spotty. No surprise, that's not something everybody does every day. But hey, there's always the source code of Android and of the AOSP telephony app if anybody wants to go really deep and want to see how they're doing things and how it should be done. There's a lot of try and error involved with many phones on your desk, calling one phone from the other one, trying to do conferencing calls. But in the end, it's impossible to test everything. And by speaking about testing, also doing automated tests when you have to have 4 or more devices calling each other is quite tricky. The question is the effort reasonable? Our clients decided that we're doing testing manually, having a manual tester instead of setting up everything automatically. And we programmed very, very defensively and tried to expect the unexpected, especially with all the events that can come in from the telephony subsystem. Regarding staying alive and awake, to help our safety features, it was really challenging at the beginning, but it was possible in our case. Luckily, we can ask for whatever permission we want and the user will grant it because it's a corporate app. It's the app the user needs to do their daily work. And they grant the permissions when they start up the app in case they've turned off some permissions accidentally. And luckily also for us, as I said, various restrictions of Android and the Google Play rules are not fully applicable for us. We've got very good support by the RSM hardware. For example, we get intents for important events from the RSM. We can receive those via statically registered broadcast receivers in the manifest. So the app gets informed about those events in any state, even if the app wouldn't be running at that moment. And as a general advice, if someone here in the audience wants to try that, before you set out to your journey like ours, make sure that all that you want to do is allowed under the distribution model you're choosing, especially if you have a consumer app and you want to distribute via the official stores. The next 2 slides contain a few useful references. Those droidcon talks were very enlightening to me. They'll also be on the slides. You don't need to write them down. You can download the slides from here. So that's all. Thank you for your attention, and I hope you've learned something new.